and welcome to this video in which I'm going to go through this AQA P1 foundation paper from June 2014. So let's start with the first question. Now, the most important rule when you're answering any exam paper is to make sure you read all the information given to you. So figure 1 shows a car with an electric motor. Really key piece of information there that we've got an electric motor. The car's moving along a flat road. Use correct answers from the box to complete each sentence. So, we've got light, electrical, kinetic, potential and sound. The car's motor transfers something energy into useful something energy. So, we know from the question stem that there is an electric motor in this car, so it's going to be transferring electrical energy. And it's even given us a clue for the next one here. Energy as the car moves. Movement energy is kinetic. Some energy is wasted as something energy. Okay, so when we've got waste energies, we'd normally be looking for thermal, but that isn't an option in this case. So the waste energy from this car, we're going to pick sound. What happens to this wasted energy? Same thing that happens to all wasted energy. It gets spread out or dissipated, if you want to use the fancy word, into the surroundings. Okay, we've then got a calculation question. The electric motor has an input energy of 50,000 joules. So that's our first key piece of information, per second. And the motor transfers 35,000 joules of useful electrical energy per second. Okay, units are the same in each time, so we don't need to worry about converting anything. Calculate the efficiency of the electric motor. Use the correct equation from the physics equation sheet. If I look at my equation sheet, I see that efficiency is equal to the useful output divided by the total input. Our useful output is 35,000 and our total input is 50,000. So we just need to put that into our calculator, and that gives us 0.7. And we could leave our answer like that, and 0.7 would give you both of the marks, or we can times by 100% to give you 70%. If you write 0.7%, that would be wrong. If you wrote 70 without the percentage sign, that would also be wrong. Moving on then to question 2. Figure 2 shows a signal generator connected to a loudspeaker. The signal generator is adjusted to change the sound wave produced by the loudspeaker. A microphone is connected to a cathode ray oscilloscope used to detect the sound waves from the loudspeaker. Here we've got 3 traces, A, B and C, produced by 3 different sound waves. The settings were the same for each trace. So we've got some tick boxes here, except they're not. Read the question carefully. Use the correct letter A, B or C to complete each sentence. People do tick the boxes on this question. Don't do that. So the sound wave with the highest frequency. To answer this, you need to know that frequency is the number of waves per second. So we're looking for the one with the most waves shown on the screen, and that's going to be A. And then the sound with the smallest amplitude. Amplitude is the height of the wave, so we're looking at B. Another calculation question in 2B. The loudspeaker produces a sound wave with a frequency of 850 Hz and a wavelength of 0.4 meters. When we're looking at the units here, we can see that it's Hertz and meters, so we don't need to convert anything. If it had been kilohertz or millimeters, we'd need to convert it into the normal unit, but we don't need to do that. So we're asked to calculate the speed of the sound wave and give the unit. Use the correct equation from the equation sheet and choose the unit from the list below. Let's start with the easy bit. Remembering the unit, speed is measured in meters per second. So once we've got that, we can look at our equation sheet and find out what the equation is. wave speed is equal to frequency times wavelength. So our frequency was 850 and our wavelength was 0.4. We just pop that into the calculator, which gives us 340. And you can just leave it like that. You don't need to put the unit again because you've already circled it. Okay, a motorbike is driven towards a microphone and CRO which are placed by the side of the road. So we've got a moving sound source. As soon as you've got a moving source of waves, you should be starting to think about the Doppler effect. The motorbike emits a sound of constant frequency. Draw a ring around the correct answer to complete each sentence. As the motorbike moves towards the microphone, the frequency of the sound wave detected by the microphone will be something the frequency of the sound wave produced by the motorbike. So if the motorbike is moving towards the microphone, the sound waves are going to be more compressed. So the frequency, we're going to have more waves per second, so the frequency is going to be higher than the frequency of the produced wave. If the frequency is higher than, our waves have been compressed together, then the wavelength for the second part is going to be shorter than the wavelength of the sound from the motorbike. Okay, question 3. Starts off nice and easy. Energy can be transferred through some materials by convection. Okay, so we're looking at convection in this question. Energy cannot be transferred by convection through a what? It's going to be a solid, and the reason for that is that in a solid, the particles are in a fixed position, and convection requires the particles to move position. Okay, figure 4 shows a fridge with a freezer compartment. The temperature of the air inside the freezer compartment is minus 5 degrees. Use the correct answer to complete each sentence. Each answer may be used once, more than once, or not at all. Okay, look out for questions that say this, because often people think there's 3 boxes, there's 3 answers, we have to use each one once. They will usually say you can use it more than once or not at all. So you don't have to use each one once. Okay, when the air near the freezer compartment is cooled, the energy of the air particles is, okay, it's cooled down, so we've got less energy, so it's decreased. The spaces between the air particles, well, that's also going to decrease because they've got less energy, they're moving around less, so they're going to be closer together. And so the density of the air is increased. Okay, it's more dense if particles are closer together. Okay. Table 1 shows some information about 3 fridges, A, B and C. They've all got the same efficiency. So when it tells us that they're using different amounts of energy, the fact that the efficiency is the same means that the proportion of energy wasted is going to be the same each time. Which fridge is going to cost the least to use for 1 year? Well, that'll be the one that's using the least energy because we pay for our energy bills. So it's going to be A. Give one reason for your answer. It uses least energy. A householder looks at the data in table 1. So someone who has a house is trying to buy a fridge freezer, they look at this data. What should they conclude about the pattern linking the volume of the fridge and the energy it uses in 1 year? So as the volume increases, the energy is also increasing. Okay, it's a simple one because it's only a 1 mark question. If it was 2 marks, it would be looking for a bit more detail. So something like if the volume doubles, the energy used more than doubles or less than doubles, something like that. Okay, the householder can't be certain that her conclusion is correct for all fridges. Suggest one reason why not. Are all fridges going to be represented by just this sample of 3? Okay, it's a small sample size, so you need to somehow indicate in your answer here that the sample size is too small. Just saying sample size is too small will do the trick. Equally, you could just say she only used 3 fridges. If you said she used 3 fridges, that wouldn't be enough to get you the mark, because it's not implying that you know that 3 fridges is a small number of fridges. Okay, moving on. Iceland is a country that generates most of its electricity using geothermal power stations and hydroelectric power stations. Okay, we're generating electricity now. Complete the sentences to describe how some geothermal power stations work. Okay, in regions where volcanoes are active, the ground is hot. Okay, simple sentence. Cold something is pumped down into the ground and is something by hot rocks. It returns to the surface as steam. Sometimes it's really useful to read on to the next sentence before figuring out what the gaps are. So something that's goes in cold and comes out as steam, that's going to be water. What are these hot rocks going to be doing to the water to turn it into steam? At a basic answer, I would say heated. Probably also acceptable because the process that turns water into steam is evaporated. If I wanted to hedge my bets and make sure I was on for this mark, I'd say evaporated. Okay, so we've got some steam now. The steam is used to turn the turbine. Okay, this is just like we've looked at loads of times in coal, oil and gas, fossil fuel power stations. We've got something, steam turning a turbine. Turbine drives a something to produce electricity. That was going to be a generator. Okay, which one of the following statements about geothermal power stations is true? Geothermal power stations use fossil fuels. Well, we've just read how they work and they don't use fossil fuels, so it's not that one. Geothermal power stations produce carbon dioxide. So in this question, there is nothing here that should be producing carbon dioxide. So this doesn't look likely, but we can't rule it out. Geothermal power stations produce a reliable source of energy. The ground is hot because volcanoes are active. Is that going to stop at any point? No, it isn't. This sounds reliable to me. We already thought that second one was a bit iffy, so we can tick that third box. What is needed for a hydroelectric power station to be able to generate electricity? So hydroelectric power is one of our 3 methods of using water. The clue's in the name, hydro. So that rules out lots of sunny days. Hydroelectric, we've got to remember, hydroelectric is the one where we build a dam on a river and the river is flowing downhill. So that makes it falling water. The long coastline is going to be useful for wave power. Okay, question 5. It's an experiment question. The student used the apparatus in figure 5 to compare the energy needed to heat blocks of different materials. So we've got different materials. Each block had the same mass. Each block had holes in for the thermometer and immersion heater. Each block had a starting temperature of 20 degrees. They measured the time taken for the temperature to increase by 5 degrees. State 2 variables the student controlled. Right, so controlled means kept the same. And we just need to look back into the question, and we've got the word the same for the first one. So that's going to be the same mass. And then the other thing that was the same for both of them was the same starting temperature. Okay, so here are the students' results. Why is a bar chart drawn rather than a line graph? Okay, this is an answer you can just remember. Whenever they ask why it was a bar chart, it's because the independent variable, the one you change, that is a categoric variable. Okay, so we've got it in different groups rather than numbers. Okay, which material was supplied with the most energy? So our graph here shows us the four materials and the time taken in seconds for them to be heated by 5 degrees. So they've got exactly the same amount of power going into them. So the one that has the most energy has got to be the one that's got the energy going in for the longest time. So that's going to be concrete. Our reason: took longest to heat. Something about the fact that the time is the biggest on that one. Okay, the iron block had a mass of 2 kilograms. Let's get my highlighter out. Calculate the energy transferred by the heater to increase the temperature of the iron block by 5 degrees. The specific heat capacity of iron is 450 joules per kilogram per Kelvin per degree C. Going into A level there. Right, so looking at our equation sheet, we can see that energy is equal to mass times temperature change times specific heat capacity. So 2 times 5 times 450. I don't even need to do my calculator because I know that 2 times 5 is 10. 10 times 450 is going to be 4,500. Okay, you can use your calculator though, just to double check. Then we've got the same apparatus being used to heat a 1 kilogram block of aluminium. He recorded the temperature of the block as it was heated from room temperature. Here are our results. So we've got the time it's switched on for and how the temperature changes. One of the students' results is anomalous. Draw the ring around the anomalous result. Right. Pattern, pattern, pattern. Oh no. Anomalous. Draw the line of best fit. So let's get a line going on here. So remember, when you're doing a line of best fit, what you want to do is make sure that you have an approximately even number of points on either side of the line. So I'm going to take it from just about here. You guys are going to use a ruler to do this. And I'm going to draw it back. Now, this line is slightly too low. All my points are above it. So I'm just going to adjust it slightly. That's better. So I've got points below and points above. Ideally, you want to use a very thin line for that. I can't change it back now. Okay, so we've drawn a line of best fit. What was the temperature of the room? So we want the temperature of the room, which is going to be the temperature it was before we switch on the heater, 20 degrees. What is the interval of the time values used by the student? So basically that's saying what's the interval between when they took readings. We can see the crosses are every 2 minutes apart. So we can just fill that in there. Okay, question 6 is electromagnetic spectrum. You know, you remember the song. So figure 8 shows that frequency increases from red light to violet light. As the frequency of the light increases, the wavelength of the light waves does what? So they're opposite. Frequency and wavelength always do the opposite thing. So if the frequency is increasing, the wavelength decreases. And the energy of the light waves, that does the same thing as the frequency. So if frequency is increasing, the energy is also increasing. Okay. Figure 9 shows what happens to the light energy when a ray of light hits a glass block. We've got 100% coming in, incident, just going in. 8% is reflected. 90% is transmitted, that means passes out the other side. So 98% is either reflected or transmitted. What happens to the other 2% of the energy? So that's got to be, it's not coming off that way, it's not coming on that way, it's got to be staying inside the block. The fancy word for that is absorbed. Okay. Beer, because all teenagers are experts on bottled beer. It will spoil if the intensity of light is passing through the glass bottle into the beer is too high. So if we want a nice bottle of beer, we need to stop light passing into the beer. Figure 10 shows the intensity of the light that's transmitted through 3 different pieces of glass. So we've got brown glass, green glass, and clear glass. Remember, this is showing the amount transmitted. We don't want it to be transmitted if we want our beer to stay good. Right, the 3 pieces of glass all have the same thickness, suggest why. It's for a fair comparison. Don't say for a fair test. They very rarely give marks for it. Okay, bottles made of brown glass are suitable for storing beer. Okay, why? Very little glass, or the lowest amount of intensity rather, is allowed through. So the least amount of light is transmitted. Okay, question 7. Electricity can be generated using various energy sources. Give one advantage and one disadvantage of using nuclear power rather than gas power. So we've got to think about those 2 in particular. So an advantage of using nuclear power, no carbon dioxide is produced. And you don't need to wait and write out the whole of carbon dioxide, just CO2. Make sure the 2 is small subscript underneath it. But the disadvantage of using nuclear power is it makes radioactive waste. Okay, next question. A single wind turbine has a maximum output power of 2 million watts. It's operated continuously at maximum power for 6 hours. What is the output energy in kilowatt hours? Right, so before we do anything else, that's in watts, that's looking for kilowatt hours. We know that 1 kilowatt is 1,000 watts. So we need to divide this by 1,000 to get it into kilowatts. So that gives us 2,000 kilowatts. Okay, so we can look at our equation sheet now and say energy is equal to power times time. So 2,000 times 6, which is going to be 12,000. Okay, why on average do wind turbines operate at maximum power output for only 30% of the time? It's a wind turbine, it's not always windy. Or if you want to be more scientific, you could say that wind is unreliable. An onshore wind farm is made up of many individual wind turbines. They're connected to the national grid using underground power cables. What's an advantage of using underground power cables? Okay, we want one. It's using underground power cables rather than overhead power cables. So what we're not looking for is, why is it an advantage to connect it to the national grid? Why connect it underground rather than overground? So they will usually accept things like overhead power cables are run sightly, or underground it's less likely to be damaged by the weather. I'm going to go with that one. Less likely to be damaged. Nice and safe underground. Biscuits. I saw the word biscuits. Figure 11 shows one way that the biscuit manufacturers cook large quantities of biscuits. Uncooked biscuits are placed on a moving metal grill. They pass between 2 hot heating elements and the biscuits turn brown as they cook. There are 2 control knobs, one for power, one for the speed of the grid. Which type of electromagnetic radiation makes them turn brown? So we're looking radio waves, microwaves, infrared, visible light, ultraviolet, X-rays or gamma rays. the one we know is heat radiation is infrared. Suggest 2 ways of cooking the biscuits in this oven to make them turn browner. Well, we've got 2 knobs we can control. So first of all, the power knob. To make them turn browner, we want more power. And speed of the moving metal grid, well, if it's going fast, they're going to be in there for less time, so we want to slow down the grid. Okay, 8C, the inside and outside surfaces. It's important that they've asked about both. Of the oven are light coloured and shiny. Okay, we're talking about radiation. Explain why. So let's start with inside. So our heat source is inside this oven. So the heat is going to come out of these heaters, and because they're light and shiny, it's going to bounce off the heater or reflect back onto the biscuits. So these types of surfaces are good reflectors of radiation to reflect infrared, I just call it IR, and the examiner will know what you mean, back onto the biscuits. Then on the outside, now remember the source of the infrared is on the inside, so we're not talking about reflection here, we're talking about whether it's going to give off heat well, and the light shiny surfaces are poor emitters of radiation, and that stops the heat being lost from the oven. Okay, question 9. Oh dear, it's a 6 marker. People get to the 6 markers quite often on the foundation paper and go, oh, I can't be bothered. But actually you probably know quite a few points for this. So, the information in the box is about properties of solids and gases. We know that solids have a fixed shape and are difficult to compress. We know that gases will spread and fill the entire container and are easy to compress. Use your knowledge of kinetic theory to explain the information given in the box. You should consider the spacing between the particles, the movement of the individual particles, and the forces between the particles. So let's start with the spacing between the particles. We know that in gases, there are large spaces between the particles. Now you've got to look out for your spelling. I'm clearly not very good at that. Between particles. Oh, and we're also after grammar, so I should have put a have in there. Gases have large spaces between particles, and solids have no spaces between particles. And how does that fact link to any of the information in this box? Well, it tells us about the compression. It tells us why the solids are difficult to compress and the gases are easy. This tells us why gases are compressible and solids, should write that out, are not. Okay, next thing, the movement of individual particles. I'm going to move that up to give me a bit more space. So in the gas, the particles are moving around randomly, and they're moving quickly. Randomly. Solid particles, well, they are moving, but they stay in a fixed position, so they're vibrating around a fixed position. Vibrate around a fixed position. Okay, now I'm also going to talk about the next bullet point before I relate it back to the box, because it's these two things together. The forces between the particles. Gases have weak, right, being fancy scientific here, intermolecular forces. All that means is between the particles. So you could just as well say gases have weak forces between the particles, and solids have strong forces. These things explain why gases got to get rid of all these extra S's. I do this quite regularly. If you're not sure about the spelling of something, look in the question. Okay, that's what I just did. I went, wait a minute, am I supposed to have two S's in gases? No, I'm not. So, explain why gases spread, but solids have a fixed shape. End of questions. Yeah, that's what we like to see. At this point, you should be going back and just checking through your answers right back from the beginning, making sure you've not made any silly mistakes. Go back through your 6-mark question and make sure that you have good spelling, punctuation and grammar, and that it makes sense. And make sure that you have filled in all of this information on the front of the paper. Okay, thank you for watching.